Well, this lecture's on Chapter 13, which is groundwater. We're going to talk about how groundwater is a reservoir for the hydrologic cycle and that it is approximately 22% of the world's supply of fresh water. We talk about porosity and permeability and how they are responsible for the movement of groundwater. Talk about the water table separates the zone of aeration from the underlying zone of saturation. How groundwater moves downward because of the force of gravity. We talk about the artesian systems and how groundwater is confined and builds up high hydrostatic pressure. We're going to talk about groundwater as an important agent of both erosion and deposition, and it's responsible for the karst topography that we have in the Irish Hills. Well, not necessarily karst topography, but the caves that develop in the Irish Hills. So here we have a picture of a cave. The cave is from the dissolution or the dissolving of limestone when groundwater is in the limestone. Actually, it's a crack that forms, and then eventually the limestone dissolves due to some of the acidic nature of water. But groundwater is all the subsurface water that completely fills all the pores and spaces that are available. And then because of that definition, it's responsible for all of the caverns and caves that we see. And we also use it as a form of fresh water. We don't drink surface water. Surface water is often very contaminated, so we drill down and we drink the water that has percolated through the ground and moved down into the water table where it's been cleaned by the surrounding rock and other minerals. As I said in the introduction, groundwater is a part of the hydrologic cycle. And if you look in this is a table from your book, you'll see that groundwater fits in right here. It's the third largest body of water for the total percentage of water on the earth, which is very interesting because it's only 0.6% of the total water. So when we talk about fresh water and its related components, that's why we're worried about the amount of water that we have, like in California or even here in Michigan. It's not a lot of water when we're talking about the total amount of water on the planet. But water basically is a renewable resource right now, but if we continue contaminating it, it'll be much more difficult to find good sources of fresh water. So groundwater is recharged when the water from precipitation in streams and lakes, which are surface waters, filtrate or infiltrate down into areas where they fill in all of that space, and that's where what we call the zone of aeration, which I'll talk about in a second. And they exit when we when we drill wells and we see where springs come out of the ground, and the expansion of the world's population and industrial development, specifically agriculture, because it's not industrial in a way, but we require a lot of the industrial type machinery to do our current agriculture. The demand for water goes through the roof, and it will continue to increase. And we've used up a large portion of a lot of the aquifers, and they're starting to become salty. So there's this real issue where water will become a limited resource when it comes to growing food, actually. There are two things going on when we look at groundwater. We have the porosity of the material that it's moving through, and then the permeability, which is the ability for it to move through those things. So porosity would be the ability for it to absorb water or hold on to water, which is, in this case, it's all of these spaces. And then the permeability of the rock is the ability for the water to move through these spaces and move down in elevation as gravity pulls it towards the ocean. And so the permeability basically is the capacity of the rocks, soils, or sediment to transmit water. And of course, permeability is dependent on porosity. But the size of the pores or these interconnections also determine how quickly material moves through the ground. For example, if we look at clay, clay is very porous, but it's not very permeable because of the water tension. The water tends to stick to clay particles, and I mean, anybody walk through clay mud knows exactly how sticky it is, so that the water doesn't move through. It actually sticks to the clay and stays there. So in this slide, table 13.1, we have a different materials, and then a percentage of porosity for each one of those materials. So soil, it's very porous. It has, 55% of soil spaces can be filled up with water. Gravel, a little less porous, which is because a lot of those stones take up space. Sand is about the same as gravel, and then silt, about the same as sand, a little less in the low end. And then of course clay, which is the most porous, but actually water doesn't move through it very well because it holds on to that water. Then of course we have sandstone, which are these rocks. We have the shale, which is it's actually an aquiclude instead of an aquifer. And then when limestone and dolostone gets dissolved, it actually is very porous. And then we have basalt and granite. The sandstone and the limestone are the most porous rocks when it comes to moving water or holding on to water. If we look at pictures of the pore spaces and then the permeability related to those pore spaces, you'll see that the poorly sorted material has a low porosity, which means a lot of those spaces are filled up with things like smaller rocks, pebbles, sand, clay, silt. So in this area you get all of this stuff that's already filled in, and the water can't, so it's less porous, the water can't actually, well actually those rocks are taking up spaces where the water would be. As far as the highly sorted or well sorted material, there's a lot of water in between those rocks because it's not filled up with some other material. Then we have these soluble rocks, which would be things like limestone, which they get cracks in them, and then the water dissolves it because there's a little bit of carbonic acid from the carbon dioxide in the atmosphere, which creates sort of a slightly acidic situation with rainwater. It's not true acid rain, but it is slightly acidic, which then breaks down the calcite or the calcium carbonate. And then we have fractures in rocks that the water can move through if it's an igneous rock. And anywhere where the water moves through it is called an aquifer. Anytime the water can't move through it, it's called an aquiclude. So aquifers allow water to move through. They transmit groundwater. Aquicludes prevent, or they're impermeable to water, so they don't transmit groundwater. Most unfractured shales, clays, metamorphic, igneous rocks, etc. are aquicludes. And this is what the water table looks like. As the water moves down through whatever material allows it to move through that has air spaces in it, you have this, what we call the zone of aeration, which right here you can see there's a bunch of air spaces. And wherein that water moves through, it's moving in this direction due to gravity, eventually reaches an aquiclude, which would be somewhere down the barrel, which would be like a bedrock, and it's impermeable to water, so that it starts filling up, sort of like a lake underneath the ground. It fills it up, and then there's a capillary fringe, which is where the water will move up due to the water tension, and it's sticking to clay or sand particles or whatever else. And so we have this area where there's some water. It's wet, but it still has some air spaces in it. And that's, like I said, it's the zone of saturation once it fills up completely. And we drill into that to get our water that we drink. And in this picture, this figure from your book, you'll see how water moves through and responds to specific structures that are underground. So here we have an aquiclude, which would be like shale. And what happens is the water moves down, it hits, and it can move this direction too. It also moves this direction, and you end up getting a perched water table, and springs come out. As this water rains on the top, comes down, hits that, comes out as a spring, and then it moves down, runs downhill until it hits where the water meets the surface of the earth, and you end up with a river. Or it could move down, and actually we can get springs that dry up, and it actually just moves down into the water table. But it moves to the area of the zone of saturation. You should also keep in mind that water moves from high pressure to low pressure. It's just like an osmotic potential. As the water moves down, because it percolates through the ground, it builds up this sort of denuded or slightly less. Denuded means reduced landform, so it follows the landform a little bit. So if you live on a hill, you can still drill down and get into the water table. But the water in that water table will move down and will move towards a zone of low pressure, which is where the rivers or lakes are, and they come out of the ground. Water generally moves about several centimeters a day, so it's not real fast, but it still is moving constantly. And like I said, springs are found wherever the water table intersects the surface. So here we have an aquiclude, the water's moving down, and wherever the aquiclude reaches the surface, where there's a perched water table in this case, these are impermeable shell beds, you end up with springs coming out of the ground, and here's an example of that right there. And it's wherever the springs intersects with the surface, or where the water table intersects with the surface, that's where you get a spring. So what happens when we drill down into the water table? We produce a zone of, a cone of depression, where it's a zone where we've depressed the water table. And what happens when you have it's often very large, but this produces lower pressure, so the water does fill in these cones, but it takes quite a long time. If this zone is like, a mile across, we made a cone of depression because we're sucking water out of the Ogallala water aquifer, the Ogallala aquifer in Nebraska. It's going to take, maybe even 100 years to fill it up. So these cones of depression can be very large. They can also end up sucking in seawater or salty water as the cone reaches an area where salt water moves into the water table, near the ocean usually. Or in other words, the infiltration rate is less than the extraction rate for the well. We do have some solutions here. I think I have a slide on that a little bit later that I'll talk about. Here we have a figure showing you what an artesian well is. So springs often will come out of the ground under pressure, and that pressure develops from the water table being at higher elevation. So you see there's a line that they have, this blue line that runs down right here, and that blue line shows you the level, or the pressure level basically. And so if your water table, as it's charged up here, which causes pressure as this moves down, you have an aquiclude right here, prevents the water from moving up. You have a hole in that aquiclude, the water is going to move up under pressure, and you're going to get a spring, or flowing artesian well. Areas where you do not reach the surface, and because the pressure is not great enough to bring it up, it's still moving up into the shaft of the well, but it doesn't get up to the surface because the pressure surface is actually below the surface of the land. And of course we have the problem of erosion. So weathering and erosion as a result of that slightly acidic water that's in the groundwater. It's in limestone areas. It dissolves the limestone and creates sinkholes. Now sinkholes really aren't something to be too worried about. I mean, I know people sometimes worry about them in Florida because there's the one individual that fell into, his house got sucked up and he died, but that's not very common. You're much more likely to get, die in a car wreck or get struck by lightning, etc. But I mean, that's kind of dark, but you get the idea. And here we have an example where we had a sinkhole form, and obviously buildings and other structures were damaged, And then we have one out in a field out here, which is, there's just a sinkhole sitting out there. There's no damage or anything, but they fill in with water often. And it's due to the precipitation reacting with carbon dioxide producing carbonic acid, which then dissolves calcite in the limestone, producing caverns. When these caverns then cave in, once the water is either the water table drops and they're no longer supported by the pressure of the water, and you get a sinkhole. Here's a picture of all of the major limestone regions and karst regions that we have. If you look right here, I'm going to draw a circle around it. If you look right here in Michigan, this is where we are, right? And right near us in the Irish Hills, we have a major limestone region, and it does have some sinkholes. They're not too dramatic, so we don't have this karst topography where you get a whole bunch of sinkholes which create these sort of rolling hill mountain structures due to the collapsing caverns. But we do have some areas where we get these sinkholes in Michigan. If we're looking specifically at the karst topography, you should see that it's a dramatic dissolution of the rock, the limestone underneath, and you get these huge caverns. So these are all caverns that sort of run through the whole thing, and they collapse pretty regularly, and you end up getting sinkholes all over the place. You get these huge solution valleys, which means there's no water in them, there's no rivers or anything, but they're areas where the river is running underneath the ground, and you get this sort of depression where it collapses as the limestone gets dissolved. Then, of course, you get these deep, entrenched sort of valleys from the caves collapsing completely, and you do get a river running through those. There are different formations that result from calcium carbonate or calcite forming on the tops of caves or in the bottom of caves. These are drips. As the water drips through the cave, that calcium carbonate will come out of solution and produce a stalactite or a stalagmite. Now remember, stalactites hold tightly to the top of the cave. That's how you remember that. And you get these columns where the stalactites and stalagmites meet, and you get entire columns that form in the caves. And this is all from the dissolution of limestone in the groundwater. And then it carries it into the caves, and you actually redeposit some of that calcium carbonate that it came out of the limestone. Here's a slide of all the different structures. So we get soda straws. They look like straws. We get the stalactite that hangs on tightly to the ceiling of the cave. You have the stalagmite. You have collapsed blocks from material falling off. And then you get the travertine terrace. And just remember, travertine, it looks like a road in a way, or a path, so you can travel on it. So travertine you can travel on. And of course a drip curtain that looks like a curtain. And these are all found in these limestone caves, and the water table, if you look right here, is much lower than the cave structures. This often is a result of water moving through these caves, and the water table will get higher and lower depending on how much rain is in a specific area. And some of these areas have rainy seasons, which means it fills up all these caverns, more dissolution of that limestone, and then they drain out, taking away a lot of that material that's in solution now, and you end up with caverns produced. A few areas of China where you can go, and they're very famous for these kind of structures. One issue that we have when we think about sinkholes is, well, us pumping out too much water to support agriculture. And this would be Nebraska, Kansas, Oklahoma, where we have all these very large cornfields or wheat fields or whatever you're thinking about when you think about agriculture. But the groundwater is a natural resource, and it can be limited if it's exploited too quickly. I mean, you pump it out too fast, you can't fill it up. And so over pumping creates a situation where you lower the water table, and salt water can come in from areas where it's salty. I mean, a lot of these, like Kansas and a lot of Oklahoma, a lot of these areas have big salt deposits like we do in Michigan, and you get low enough, that salt water or that salt will get into the water and start moving into the areas where you're going to pump it out on the fields, and it doesn't work. Then you get subsidence, which is sort of like, think of it like where you pull out all of the water, and all of those spaces that are open collapse or get compressed, and it becomes denser, and the land actually drops in elevation. And then of course there's contamination from other agricultural stuff. This is actually some concern we have for the Keystone Pipeline, because it's going to go right through the Ogallala, which supplies us with something like 30% of our food for the United States. It's a very large amount. And then we have problems where salt water can move into an area. In this case, we're talking about saltwater incursion from the ocean, whereas if you're pumping, right, you have a pumping well and you start pumping, you pump out saltwater is denser than fresh water, so that's why it's above the saltwater here, but you start pumping in saltwater because you pull it in and you start pumping it up faster than the fresh water can filter back in. So what you do is we make a recharge well that's at higher elevation, you pump it in, and then you pump out the water at a different area where you need that fresh water. And as a result of pumping out water, we get, some features that are very famous, like the Leaning Tower of Pisa, which is, due to subsidence, we've pumped out, the water was left from this area, and the ground drops in elevation, and it ends up pulling the Leaning Tower of Pisa in one direction. And actually, the water, we pumped out the water on the other side, and the Leaning Tower of Pisa is actually moving back to an upright position, which is kind of interesting. And then, of course, if you look here, this is from in your book, but it's from 1925 right there. And then they took the elevation again, 1955, and here we are in 1977. And in some areas, this is the Ogallala. This is what I was telling you about before. Is the Ogallala, we pumped out so much water that basically we pumped out the equivalent of Lake Michigan out of the Ogallala, which is, where a lot of our food comes from, and we can't return that water. And so the land has dropped up to like 50 feet. So it's quite a interesting problem. The other issue, like I said earlier, was we have contamination problems. As we pump out water, which creates suction in a sense, we'll recharge it. We need it recharged. And if we have landfills they're supposed to be covered in cement or some lining that is an aquaclude, but some of them are not, which means a lot of that material moves into the, at number 1 here we have water draining through the landfill into the groundwater, and then we have a well, just like we do in Michigan down here, number 3. So people are pumping out contaminated water, even though they don't know it. It could be filled with arsenic, which is a real problem. That's a natural element that we find in our water around Michigan. And then, of course, it gets into the marshes. But one thing interesting about marshes is as the water percolates through, marshes are very good at cleaning any contaminants. Fortunately, it gets into the wildlife and other things, but they do clean the water very well. That's why we like marshes. That's why we protect them, because they're part of the watershed and they clean a lot of the water that we drink. But basically, excluding pollution from us, groundwater quality is determined by the kinds of materials that make up the aquifer. So if it's rocks containing arsenic, you don't want to drink the water. It's also the amount of time that the water is in the aquifer for cleaning, and then the solubility of the rocks and the minerals that are in the aquifer. And these factors account for most of the hard water and iron staining that we have in Michigan. I know you guys drink the water, sometimes it tastes kind of icky. Well, that's because it's got a lot of dissolved minerals and stuff in it. Most of the so it's just perspective here. If you look at the total amount of calcium carbonate, magnesium, iron, other things in the water, and it exceeds 120 milligrams per liter, the water is considered hard. If you look at the water that we get out of a lot of the wells around here, it can be upwards of 600 milligrams per liter. So it's pretty hard, the water that we have in Michigan, if you don't use a water softener. And that creates problems for our homes because they fill up with scale and other stuff. And so that's why we tend to soften our water that goes into the water heater and other things, so that it actually increases the life of our pipes and their water heater itself. Some of the hardest water that you'll find are in hot springs or fumaroles, which are steam discharges in volcanically active areas, and hot springs are basically where the water makes it to the surface and not just the steam. And it's basically it's higher than human body temperature. Obviously, it's right at the point of boiling, 100 degrees C, and we find some really interesting critters that live in these kind of pools and ponds. Here we have an area that it's like Yellowstone or something. I don't know. It's from the book, but the people are standing here. This yellow is sulfur. It can also be a red from different organisms that live in these different springs. And there's a lot of copper deposits or nickel or other things that you see. That's why it's kind of green. And what happens is as this water moves out from the area that it comes through all of these rocks and dissolves all of these different metals and stuff at high temperature, and then as it gets nearer the surface it cools down and it can't hold that amount of metal, and so it drops out of solution. You can often mine areas that these kind of hot springs have moved through the earth for a long period of time. They end up, think of the Bingham copper mine. It's a result of the North American plate moving over where Yellowstone used to be, and that's all a bunch of copper and gold and a bunch of other stuff that's all through the land right there, and that's old volcanic activity from a very long time ago. We're talking probably millions of years ago. And they've now dig it up and use that ore to make copper and gold and get a bunch of other metals out of it. And here we have a picture of that travertine. Looks like steps. And we also call it calcareous tufa, which is, just the same thing as we call travertine. And it's a calcite that precipitates from supersaturated. When I talk about these different metals, it's a supersaturated situation. They're high temperature, which means at normal room temperature it doesn't stay in solution, so you produce these really interesting sort of deposits. And of course, this is yellow. And another deposit that's pretty interesting is a silicate deposit. So this would be like sand. It's heated up, but it's in solution, which silicate's very hard to get into solution. It has to be very hot, and it's super saturated. And then it's called geyserite, which is a silicate. So think of it as like sand that was in the water, and then it cools down as this geyser, and it's obviously less it's harder than the surrounding land here, which is probably calcium carbonate that's dissolving, and then the silicate that's in this geyserite hot spring deposit here is just, well, it's eroding much slower, and so that's why you get this sort of this stand of silica just out in the open. And then if you ever go to Yellowstone, we have the geysers. Now the geysers are pretty interesting because they work like clockwork. And the reason they work like clockwork is the water that fills in these areas is the same amount. It changes, it slows down over time, but what happens is as the water fills up, as it percolates in from the water table, it reaches a flash point where suddenly it starts boiling, and as you release the pressure, because this water starts boiling off and coming out, more of it boils, which means you release more pressure. And so they tend to, because of the area of each one of these chambers, it stays pretty much the same. It does, like I said, slow down over time, but it takes many hundreds of years to do that because you're dissolving these caves. We have Old Faithful, which means it erupts every, 12 minutes or whatever is the correct time for these areas and the amount of area that the water's filling up.